Okay, so these are the two problems we looked at in the tutorial, question 1 and question 2. And the method we used for number 2, finding all the solutions, say to that equation 5n was 12, that was a good kind of overall method, a general method which we could apply to any problem of this type, finding all the solutions to 5n equals some number. Okay. Now, I've saved the pages from that tutorial actually, so I'll get versions of those up on the G+ page as well. Now we're going to look at another important aspect of phi. So phi, remember, you can think of it as in two ways. So it's got its definition that 5n is the number of integers between 1 and n that are co-prime to n. So it's a function that is counting the number of numbers less than n that are co-prime to n. But of course, from what we've seen already, that is also the size of the multiplicative group of congruence classes modulo n. It's the number of elements that are in this group. And it's that aspect about it which we're going to concentrate on today. So we're going to come back to looking at this group, and we're going to make use of a result about groups that we have. Well, we mentioned it briefly, very briefly, in the first year Maths Fundamentals last year. That's this idea, if you have a group, so we're thinking of G as being our Zn times here. If you have a subgroup of that group, so a smaller group living inside it, the possibilities for the size of the small subgroup are restricted. The only possible sizes of subgroup that you can see is where the size of the subgroup is a divisor of the size of the overall group. Okay. So straight away that tells us that in the multiplicative group of congruence classes modulo n, because that has size phi of n, means the only possibilities for sizes of subgroups of that group is has to be a divisor of phi of n, okay, a factor of phi of n. So what are the subgroups we're going to be talking about? Well, we're going to focus on subgroups like this, these cyclic subgroups generated by a particular element. Okay, so I just want to talk through that a little bit on the page. Okay, so if we've got let A be an element from Zm times. Okay, so A is a congruence class modulo m, say. Or you can think of it in terms of A as an integer between 1 and m. It's co-prime to n. But strictly speaking, A is a congruence class modulo m. Then the subgroup generated by A is written as, using this angle bracket notation. These are two angle brackets, like a less than and a greater than sign either side of A. And this simply consists of all the powers of A, like this. Okay, every integer power of the element A. And when it's written, it kind of makes you think that there might be an infinite number of things in there. But of course, the group Zm is the group we're talking about is finite. Okay. So remember, the order of this group is 5m, so it's just a finite number. So you can't have an infinite set inside a finite set. So it must be that this thing actually consists of a finite number of objects. So another way to think of this is it's going to be 1, which is the same as a to the power 0, or the congruence class of 1. It's going to be a itself, a squared, a cubed, etc. But because you've only got a finite number of objects in Zm, sooner or later, these powers, you're going to have to come back and hit the start of this list again. Okay? So sooner or later, you're going to find say, an a to the r, and then there's going to be, when the next power you look at is going to be 1 again. Okay. And if you keep looking at increasing powers, this is only going to go back through these congruence classes again. So if a to the power r plus 1 is 1, then a to the power r plus 2 will just give you a again, because you're just multiplying a to the power r plus 1 by a to get a to the power r plus 2, so, and so on. So there's a certain cycle of elements that you go through. So let's eliminate the duplicate we have here. So you got a cubed. So it goes up as far as a to the power r, and a to the power r is the last distinct one you get, okay? So the group generated by one of these congruence classes is just going to have a finite number of things in it, okay? And by Lagrange's theorem, the order of this subgroup, i.e. the number of things in it, which in this example here, how many things are here? There's r plus 1 things in it there, as we've written it there, because we're counting 0, 1, 2, 3 as far as r. This must be a factor, the size of the containing group itself, which we know to be 5m, okay? So you can write it like this: the order of the subgroup must be a divisor of the subgroup. Okay. So note that we have a to the r plus 1 is equal to 1, the identity in the group here. Okay. And so that tells us that if you look at the corollary there to theorem 5.6, it says that if you've got a finite group of order n, so for us this will be this finite group here of this order, 5m. If you've got a finite group of order n and you've got an element in the group, then when you raise a to that power n, when the exponent you raise a to is the size of the group itself, that means you must get the identity. You must get the identity back again. Okay, you can look at the proof of that. That's just a simple argument based on this fact about divisors. So let's look at this corollary. So we've got G being a finite group, so you can think of G as one of our multiplicative group of congruence classes. You've got an element A from the group, and you're going to raise A to the power n, where n is the size of the group. So the n is like our 5m. So as we've just said, by Lagrange's theorem, unfortunately I'm using r here instead of r plus 1. But by Lagrange's theorem, this number r, well, this r is the size of this group. So r is the number that you have a to the power r equals the identity, or the equivalent thing I had on the visualizer page there was a to the power r plus 1 equals 1. Because that is a divisor of n, when you raise n to that power, because this number r, the order of the subgroup, divides n, you can write n as q times r, some other integer times r. So you've got a to the power qr, but then you write that as a to the power r times q. But because the a to the power r is the identity, or 1 in the context of these multiplicative groups of congruence classes, you would just be raising 1 to some power, so that's always going to be 1, always going to be the identity. Okay. So in the language of groups, the multiplicative groups of congruence classes, well, back to the language of integers, this becomes this result, okay, which is attributed to Euler. And that's if you've got n being a positive integer, so n is the modulus here. You've got a number a which is co-prime to n, so that means a represents an element of the multiplicative group of congruence classes. When you raise a to the power 5n, you always get something congruent to 1. Okay. We'll be looking at applications of that in a moment. We've already kind of looked at applications of that before, but we'll see it now shortly. Now, a special case of this has got a well-known name of Fermat's little theorem, to distinguish it from Fermat's last theorem, of course, which is anything but little, has a huge proof. But Fermat's little theorem is just a special case of this result in the case where n is a prime number. When n is a prime number, remember, phi of p, so when n is a prime number, so this is going to be phi of p here, phi of p is p minus 1, okay? When the number p is prime, everything between 1 and p minus 1 is co-prime to p, okay, because p is a prime number. So the special case of this is that we have a to the power p minus 1 is congruent to 1, okay? So these are the two, these two results, theorem 5.7 and its corollary there. These are the two results that we're going to take away from this. And we'd like to look at some applications of these now and how they can help us work with certain large integers, okay? So important results are this thing that if the GCD of A and N is 1, so i.e. that's telling you that the congruence class of A is an element of Zn, is an element of the multiplicative group of congruence classes, then a to the power phi of n is congruent to 1 modulo n. Or in the, yeah. And the special case of this, Fermat's little theorem, is that as long as p does not divide a, so if p is a prime, as it always is when we use p in this course, as p is a prime, and as long as p does not divide a, so that ensures that you've got the co-prime property, then a to the power p minus 1 is congruent to 1 modulo p. So the key thing about these results, so the key application of these, is these allow us to simplify exponents, reduce exponents when dealing with congruences. So let's figure out an example. Let's take, let's tackle this problem. What remainder is left when 2014 to the power 1975 is divided by 39? Okay, that's a question. These dates are dear to my heart. Of course, that's the year I was born. This is the current year, and so that means I'll be 39 by the end of this year, after my birthday. So as stated like that, it's a horrible problem because this number is huge. We certainly don't want to try and figure out what that number is, okay? It's not, of course, it's not, the computer can do it easily, but I'll soon show you an example where the computer just falls over and refuses to work, but we can still figure it out. So, you know, we can't possibly hope to deal with that number itself. So we'd rather deal, we need to simplify it somehow. Now, but we're talking about remainders after division. So this question becomes, we've got this number, 2014 to the power 1975, and we're trying to work out its congruence class modulo 39. That's the point. Okay, so this is how we do it. Well, first of all, we work on the base. we're looking at powers of 2014, but because we're only talking about congruence classes modulo 39, we can replace 2014 with its congruence class modulo 39. Okay. So I've loaded up. Oh God, nothing's working for me today. It is. Okay, we'll try and go something. I hate defaulting to Wolfram Alpha when I can't go on to Sage for some reason, because Sage is infinitely better. But something about I'm not signed in properly there. Anyway, so we'll go 2014 mod 39. So what's that? So that's congruent to 25. And that's true since 2014 is congruent to 25 modulo 39. Okay. Okay, so that simplifies the problem somewhat. But still, 25 to the power of nearly 2,000 is still unreasonable to do. So now we want to start thinking about how we can work with the exponent. But we're going to apply this result from Euler's theorem that we have. Okay. So first of all, we need to work out the Euler totient function of 39. And we have a formula for working out phi values, which is built in the prime factorization of the argument. So 39 factorizes as 3 times 13. So its phi value is going to be 2 times 12. Okay, just the product of one less than each of those primes. You don't have any power of 3 or power of 13 appearing here because they started off at power 1. So you reduce the power of them and stick that new power over here. But they were already at power 1, so when you reduce them, they just become 1. So it's just 2 times 12, which is, well, we can work that out, it's 24. So by Euler's result, we know that 25 to the power of 24 is going to be congruent to 1 modulo 39. So that means that whenever I raise 25 to the power of 24, we get something congruent to 1. Okay, so we can use that to simplify this problem of working out 25 to the power of 1975. So we need to break down, and we need to simplify 1975 in terms of 24th. I.e., figure out what it is congruent to modulo 24. Remember, the 24 is phi of our original modulus 39. So has anybody worked it out? Got it on the front? No. So what do I want? 1975 modulo 24. 7. Okay. Now we can kind of rehash the proof of this Euler's result a little bit. So i.e. 1975 is some multiple q of 24 plus the remainder 7, some q. I don't care what the q is. So when I work out 25 to the power 1975, as I'm trying to do, that's equal to 25 to the power q24 plus 7, which is equal to, so I want to write it like this, 25 to the power 24 itself to the power q, and that's multiplied by 25 to the power 7. So I'm just manipulating indices, no problem with that. But once I pass to congruences, modulo 39, then Euler's result takes over. 25 to the power of 24 is congruent to 1. So that's 1 to the power q times 25 to the power 7. So in other words, it's just 25 to the power 7 modulo 39. So what was a kind of, well, for us in the space of the hour, what's available to us here is an intractable problem. Like, we can't possibly work out 25 to the power of 1975. Too much paper needed, too much time needed. But suddenly now, by applying these results, we've reduced the problem quite a long way. Now, the congruence class we're looking for is the same as the congruence class of 25 to the power 7. Okay, so that's much more doable. Yeah. So 25 to the power 7. Well, you know, if you'll allow me to use the calculator to do that, 25 to the power 7. But the handheld calculators do that. Yeah, so it surely can't be that big. Yeah, so a handheld calculator could certainly handle that. It's just 6 odd million. Or 25 to the power 7. I mean, you could work it out. There is a way to go through it. Oh, it's congruent to 25. Okay, so 25 is the answer. 25 is the remainder. So 25 is the remainder. After dividing 2014 to the power of 1975 by 39. Okay. Now, of course, I was just being lazy going back to the calculator there. I mean, even working out 25 to the power 7, you could still do that. That's still quite doable just with paper, because you'd square 25. Should know what that is. What's 25 squared? 5 to the power 4. I should know that off the top of my head. Anyway, whatever it is. Anyway, you can square 25 and then immediately reduce it modulo 39. And then multiply that answer, which is be less than 39, by 25. Reduce it again. So, I mean, you can work this out by never going above a number. I mean, you'll never reach a number much beyond 39 by 39. Okay, you know, you'll never encounter a number above a few hundred. Okay. Whereas to tackle the original question, 2014 to the power 1975, you know, that's kind of astronomical number yearly. Okay, so this shows us a good application. It's a nice application. Nice application of how using phi of n simplifies exponents modulo n. You know, simplifies, let's say, powers of numbers modulo n, like we were trying to do here, 2014 to the power 1975. Now, of course, while your calculator would probably struggle, while your little Casio job would probably struggle to do 2014 to the power 1975, of course, it's not really that big a number. The computers can easily handle it. 2014 to the power 1975. This is really what I wanted the Sage for it to do. Trying to, you'll see I'm not signed in, right? Just signed in. I'll sign in quickly because it's a much nicer interface. But anyway, that's, well, actually, this will show it to us exactly, actually. So there it is. It's not too big. Well, it's kind of loud. Oh, let's put a dot, 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 actually, so it's not showing us all this. Yeah, there's no dot, dot, dots there. So that's the actual whole number. It ends as 624. That's the whole number. It's a big number, but it's working with its exact value there. It can manage to do the computation. And indeed, Wolfram Alpha would probably tell us this original answer. If I wanted to know this, modulo 39. So it can confirm the result for us at 25. But what if we made it a bit more interesting? So I was born in 1975 and my dad was born in 1945. What if I wanted to do 2014 to the power of 1975 to the power of 1945? Well, okay, so Wolfram Alpha has, okay, it's fiddling around with the number, but the number is far too big to contain in its memory exactly. It can show me what the first few digits of it are. So it begins 2494. You can work that out. And it ends this, but it can't possibly cope with all the stuff in the middle because there's 10 to the power of 6,000 digits, and that's just silly. And Sage, of course, won't do much better. Hopefully I won't break it. It should probably detect that it's trying to do something unfeasible. Yeah, it says error. How does it say that? Exponent must be at most. So that's actually the largest exponent it can deal with. Exactly. It was, it can cope with. Interesting to see if it can. I want this to refuse to give me the answer as well. No, so it is a little bit clever. It has figured out that this result is 25. So actually, Wolfram Alpha is knowing some good stuff here. I'm hoping Sage can do it too. It's facing some problem. Oh, that's pretty. But how would we do that one? Using our theory. What about 2014 to the power 1975 itself to the power 1945? What about this modulo 39? How can we work out the representative of this? Well, we can proceed as before. We need to know the power of this exponent. We need to know the congruence class of this exponent modulo 539. So we'll need the congruence class of 1975 to the power 1945 modulo 539, which we saw was 24. But of course, that is a problem we can't deal with directly. So we now apply the simplifying approach to this. To this problem. Now, I can instead replace 1975 by a simpler representative modulo 24. I replace it with what it's congruent to, modulo 24. So 1975 mod 24. I should probably do that in my head, but 1975 mod 24 is 7. That's nice and small. 7. Okay, why is that true? That's true since 1975 is congruent to, sorry, it's congruent to 7 modulo 24. Okay. But it's still 7 to a huge exponent. I want to simplify that. But now this is a power of a congruence class modulo 24. So to simplify this power, I need to pass to phi of this. So this is going to be phi of 39. I need to know phi of 24 now. So to reduce the 1945, to reduce the exponent, I need to know phi of 24. Well, to know phi of 24, I need to know, what's 24? 8 by 3. So it's 2 cubed by 3. That's its prime factorization. So using the product formula for phi, this is going to be 2 squared by another 2. So the 2 squared comes from reducing the power of 2 by 1. It becomes 2 squared. And then you get an associated factor, which would be 2 minus 1. This is 1, so I don't bother writing it down. Then this 2 comes from, well, I reduced the power of 3, but it's already 3 to the power 1. So it goes to 3 to the power 0, which is 1. So again, I haven't written it down. But then I get the associated factor 3 minus 1. So that's this 2. This 2 is coming up. So it's 8. So phi of 24 is 8. So that means I know by applying Euler's theorem that 7 to the power 8 is going to be congruent to 1 modulo 24. That's what the result about phi, the result concerning the Euler totient function gives me. We can actually do a bit better than that. We can actually get an even better result than that. Just with a little bit of observation. Can I improve on that 8? Improving on it means get it lower down. This is probably why Wolfram Alpha was able to get the answer so nicely. Well, if you think about powers of 7, once you go to 7 squared is 49. Modulo 24, 49, quickly spot that that's 1, isn't it? Because 49 is 1 bigger than 48, which is 2 by 24. So actually, from observation, which we can do because the number is small, you know, we wouldn't be able to observe it if the number 7 was any higher. From observation, 7 squared, which is 49, this is already congruent to 1 modulo 24. So this is still true. It's still true that 7 squared is congruent to 1. Sorry, 7 to the power 8 is congruent to 1. But it's not the first time that a power of 7 gets back to 1. In fact, there is only one non-trivial power of 7. 7 to the power 0 is 1, which it always will be. 7 to the power 1 is itself 7, but 7 squared is already back to 1 again. So actually, I can simplify my 1945. I'd be looking originally to simplify it modulo 8, but actually, because I've noticed that I've actually got a 2 there, I can actually simplify it modulo 2. And 1945 is definitely congruent to 1 modulo 2, because it's an odd number. Things are either congruent to 0 or 1 modulo 2, but 1945 is odd, so it's congruent to 1. So that means 7 to the power 1945 is congruent to 7 to the power 1 modulo 24. And that's just 7 modulo 24. Now this number, this 7 to the power 1945, this is the That's really this exponent up here. So the original problem, we can say reduces as, so we'll just quickly summarize it. It was 2014 to the power of 1945. No, to the power of 1975 I did first, then to the power of 1945. I now have this as congruent to 2014 to the power 7 modulo 39. Because the 1975 to the 1945 is congruent to 7 modulo 24. And what was the 2014? What was that congruent to? 25. So I now have this as 25 to the power 7 modulo 39, which is the power of 25 we had before. So this is still congruent to 25 modulo 39. Okay, so these examples show how phi of the appropriate value, how it works to simplify the exponents when you're trying to figure out the congruence class of a power. Okay? And that is the method by which Wolfram Alpha was able to say what we had a couple of applications ago. Yeah. So how was it that Wolfram Alpha was able to answer this question? Congruence class of this huge thing modulo 39, it was able to answer it as 25, even though it couldn't possibly deal with the number itself. 2014 to the power 1975, power 1945. I mean, it looks kind of impressive, like it's capturing the number. You can see the front of the number, you can see the end of the number. But of course, the distance between the front and the end is 10 followed by 6,500 zeros, digits long. So it wouldn't fit into the universe, probably. It'd just be, for whatever way you wanted to record that number, it'd be pretty big. It certainly wouldn't fit into the galaxy or anything like that. However you were to try and write that number down. Okay. So it shows, it shows the kind of power in some sense that these things give you. So that kind of brings us to the end of that that chapter. I mean, there's a few little things a few little exercises there. I mean, we've come quite far with the function phi now, so I'm hoping you're confident enough about applying the product formula, but you should make sure you are comfortable with applying the product formula in term 5.1. I think we've covered this. What is 5p when p is prime? It's just p minus 1. There's a little result here about phi of n. It looks quite similar to the one we did in the tutorial. May even be a restatement of it. No, I don't think so. No. You're trying to show that phi of n is a half of n, if and only if n is itself a power of 2. But you can certainly do that using a similar approach to how we did the similar sounding problem, which was phi of n was phi of 2 times n in the tutorial. Questions 4 and 5 are just a couple of applications of this result we've been applying here with the examples all the time, about simplifying large powers with reference to the size of these groups. And a similar little problem with powers of 3. Well, the following chapter and what occupies the kind of next part of the course, really, and there's a couple of chapters on this, is we're going to get down to the general problem of solving problems like this. Being able to solve polynomials modulo a certain modulus. Okay, so just as there are formulas for solving quadratic, cubic, quartic, polynomial, and so on, certain modulus. Okay. So that's the general problem we're going to be tackling next in the next couple of chapters. Okay. So we'll pick that up next week, I guess.